Once you use that event code, so you should be on this page. Yeah. You need to click on this start button. Basically, the structure of the course is like this. Uh, it's building transformer based NLP applications. Then three parts are there for this. The very first part is the basic machine learning. This machine learning is in NLP. Then second part is basically focusing on BERT and how it provides the self supervision. Then the last part is the deployment issues. Okay, and on this basis we are having two assignments. One is the first MCQ question. You can see here the MCQ question. It is of 30 marks out of 100. Then one coding assignment is there, which is of 70 marks, in which several fixed me's are there. Those fixed me's needs to be replaced. So we will see these notebooks one by one. First of all, you can just click on this start button. So once it is getting loaded, then meanwhile we will see the presentation, and then we will come back to this notebook once again. Yeah, this is the agenda of full course. First part is very simple. Basically, just introducing how NLP is relevant for machine learning and deep learning field. So here we will see what is exactly NLP, what is its problem formulation, how texts are represented, various techniques for reducing the dimensionality, then embeddings and recurrent neural network. And the backbone of the entire NLP is nothing but that attention model, because all these transformer models that are introduced in the lab of this part one are based on attention mechanism. There are various NLP tasks, like natural languages are involved over here, uh, like we can say English, German, French, Hindi, Malayalam, Telugu. Okay, and these are the various several NLP applications. Where examples are sentiment analysis. Like suppose input is given to us, and we are interested in finding the associated sentiment with this, whether it is positive sentiment or negative sentiment or neutral sentiment. Then intent detection, common sense reasoning, emotion detection, sarcasm detection. All these are the applications of NLP. Specifically, in literature, it is represented with the help of this NLP task. So ultimately, you can imagine that the text or the textual input that we need to provide as input to the model, and it will predict something. Okay, this is what machine learning model does. But before processing the input, what several types of pre-processing that will be required on the text. We cannot directly give input text to the machine learning algorithm. It will not understand what is this text is all about. So there are several pre-processing. The pre-processing of text, such as cleaning the data, removing some full stop, commas. Okay. Then how do those pre-processed text are represented? Is there some sort of reweighting that is required for various parts of the input? Then what is the dimensionality of the input, whether it is very large, so that we will be requiring that dimensionality reduction techniques, because we are not interested in processing that much large dimensionality due to the limited amount of compute and limited amount of memory available with us. Then some vector comparisons are there. So all these things are nothing but comes under the pre-processing part. Ultimately those texts are represented in terms of numbers, and those numbers or vectors of integers or float, that is given to this machine learning algorithm, and it understands those numbers or floating point numbers. Now here we can see there are various
Excuse me, sir.
algorithms for this kind of representations. The entire structure is divided or categorized into two parts. One is this representation, and the last one is the machine learning algorithm. So machine
So the
learning algorithm is the
presentation,
last part.
so the presentation screen is not visible.
Yes, sir, it is stuck.
Now it is visible. Just let me know whether it is visible or not.
Not yet.
Okay. Now it is visible.
Yes,
Yes,
sir.
yes, it's visible.
So basically, what I was telling you, like first of all, the input text that is provided, this should be pre-processed, and it should be represented in terms of or in the form of numbers, so that this ML algorithm can understand this what the input that we are providing it to it. Yeah. This is remaining. The various standard algorithm for this kind of representations are known as global vector, and word2vec. Okay, and all these algorithms are used for this pre-processing part and representation part. Text pre-processing, text representation, reweighting, dimensionality reduction, and vector comparison.
Can we start from the start? I wasn't able to understand that part due to the technical error.
Hello.
Sir, can we start the starting? I wasn't able to understand the first part due to the technical error. The screen wasn't visible. So, can we do it from start?
Your audio is not coming clear, or otherwise, can you type in the chat box? Okay, so I will explain these things once again. No issue. And see, simultaneously, what you can do, you can just start this coding assignment. Sorry, this assessment questions, and then we can see this assessment can also be solved simultaneously or not. So I will explain these things. This is what NLP applications and NLP tasks are about. Some natural languages are involved over here, such as English, French, German, and the various examples of NLP tasks are, suppose, sentiment analysis. Like suppose one input is given to us and we are interested in finding the associated sentiment from that input, whether positive sentiment or negative sentiment or neutral sentiment is involved associated over here. Similar type of applications or NLP tasks are emotion detection, sarcasm detection, etc. Now the problem formulation is this: the textual input, or suppose one sentence is given as input to machine learning algorithm. Now this machine learning algorithm will predict something. This is overall scenario is all about that we understood from machine learning in NLP examples. Okay, but this is not the thing. There are various pre-processing that needs to be done before giving this input, before giving the text to the ML algorithm. Some pre-processing that might be required, like suppose removing the column, comma, removing the semicolon from the text. So cleaning the data, pre-processing the data, that is the first main part. Then this second part is how these texts are represented in terms of numbers, or in the form of vector. Then some reweightings is required or not. And then we will check the dimensionality of the input data. If the dimensionality is very large, then we are not interested in processing that large amount of data, because we are not having enough computational capability, as well as we are not having a huge memory available with us. That's why we go for the dimensionality reduction techniques. Then some vector comparisons are there. So broadly, you can categorize, or you can classify everything into two parts. One is that this first representation and pre-processing part, and second one is the ML algorithms. So ML algorithm is the last part, which is taking care, which is coming last, and all these algorithms are all these parts are completely based on some of the text representation algorithms. So specifically, we can we are mentioning two main text representation algorithm. One is that global vector, and another one is word to vec. Okay, so these two algorithms are there, which is working at the back end, which are responsible for all this kind of representation and vector comparisons, etc. So basically, we are categorizing the entire thing into two parts. One is that subset of this word representation. So this is nothing but our representation, first part, and second one is nothing but the approach that we are using, which algorithm that we are using. Now text representation. So the very basic algorithm comes under the category of text representation is nothing but a bag of words. So basically, we consider that words are there in a bag, and we will just identifying the frequency. Suppose just look at this. This is one sentence, and we are just calculating the frequency. D is occurring 2 times, cat is occurring 1 time, quickly is not occurring. Okay, so this is nothing but overall vocabulary, and we use one hot encoding for this. What do you mean by one hot encoding? So suppose our vocabulary is having 100 words, then if it is a first word or the word is occurring at the very first place in the vocabulary, then this is the very first entry in the vector will be 1 and rest all will be 0. If the word is occurring at last position in the vocabulary, then the last entry in this vector would be 1 and remaining all will be 0. If the word in the vocabulary is occurring at the second position, then the second entry in the vector will be 1 and rest all will be 0. This is known as one hot encoding. There are various problems with this one hot encoding. It does not capture the semantic similarity. What do you mean by this? Like suppose if we calculate the cosine similarity of these two vectors. Okay, so dog and cat, these are similar because they are similar kind of animals. But if you look at if you perform the vector multiplication of both of these two vectors, then it is comes out to be 0. And on the other hand, if you perform the dot product of dog and some red, then that is also 0. So it is not capturing the semantic similarity. What do you mean by that semantic similarity? We want that king and queen, these two words are similar. Some royalty is associated with these two words. Okay, so these if we perform the dot product of these two vectors, then this should be closer, and if the dot product should be high, that's what we want. So we go for a distributional representation. Here just look at this. Everything is starting from this co-occurrence pattern. So what we will do, we will just mention one matrix. This is x-axis, this is y-axis. On x-axis we are writing the word, y-axis we are also writing the word, and we are just writing like how many times d is occurring in the context of bug, 8 times. How many times bit is occurring in the context of back, 2 times. This is nothing but the our co-occurrence matrix, and it is written on the basis of our input data, right? And now the things are getting started. Like suppose if we are interested in representing this little, then this column will represent little. If we are interested in representing back, then this column, last column, will represent back. This is the overall idea. So here, this example is word to word. On x-axis word, and on y-axis this is also word. But it's not the only relationship. It can be word to document. So here on x-axis we will writing the word in the vocabulary. On y-axis we are writing the documents. How many documents we have? Okay, and this relationship is known as word to document. This second relationship is word to word that we have just seen. Then word to user person, word to user behavior, word to product. So here these are very simple relationship, and these are not the only metrics that we can use. Here word to user and user to product. So what we can do in this two-dimensional data, we are introducing one more axis in z direction, and then we are introducing product. Word to user is already there, and then now we are introducing the product, and based on that we will represent the word. There are various techniques for dimensionality reductions. Basically, latent semantic analysis uh, is the most commonly used. Uh, if we go in the detail of this, then singular value decomposition takes place. Ultimately, some matrix is given to us, and which matrix? That co-occurrence matrix. Fine. And in that co-occurrence matrix, if we calculate the largest singular values, like suppose 10 largest singular values, and if we perform, or if we calculate the eigenvectors corresponding to those 10 largest singular values, then every information that is important can be represented with the help of that reduced dimensionality. Just look at this here. We are finding the k largest singular values, and after that it is represented like this: x is equal to tk multiplied by sk multiplied by pk transpose. Okay, If you perform the multiplication of these matrix, then the resultant matrix dimensionality is same, x. Initially, suppose just imagine that this T is 100 cross 100. Okay. Now this time we are representing, we are just calculating 10 important singular values. So this is represented by 100 cross 10. Okay. Now this sk is something 10 cross something, so that matrix can be compatible to multiplication. Basically, our aim is that documents which are similar, that should be closer to each other. Now coming back to the embedding part. See what is the meaning of embedding? Basically, these words are embedded in some predefined space, predefined dimensionality space. So, like suppose vocabulary is there, the size of that vocabulary is 1000. Okay, means 1000 words are there in this vocabulary, but we are not interested in representing these words with the help of this 1000 dimensional vector. And we define that, okay, we will represent the word in a lower dimensional space, such as 100 dimensional space. Then what you will do, you will embed each and every word from that vocabulary into 100 dimensional word, and it will be a distributed representation, which is much more compact, much more efficient as compared to one hot vectors. The standard algorithm that can be used for this is nothing but word to vec. So basically two types of implementations are there for which comes under word to vec. One is continuous bag of word and another one is skip gram model. So this was proposed by in 2013, and it's a linear model. Basically, everything is learning in unsupervised manner. So no labeled data is given to us. The only difference between continuous bag of word and skip gram model is that in continuous bag of word, one center word is predicted with the help of surrounding words. Okay. So here these are the surrounding words: first, second, then third and fourth. Based on the surrounding words, we are predicting the center word. In skipgram model, we are predicting the surrounding words based on the center word. See, center word is same. Cat, everywhere cat is there, and we are predicting the surrounding words. Fine. Our first thing is that not encoded vector should be represented to some d-dimensional with the help of embeddings, and we need to refine these embeddings with the help of learning process. This is what ultimately we do. Then some glow is there, global vector. The idea behind global vector is that dot product is proportional to the probability of co-occurrence. Like if the probability of co-occurrence of two words are high, then we want that if you perform dot product of these two representations of vectors, they should be high. This is what ultimate aim behind this. We can also compare this glow with word to vec. So this is nothing but first word to vec implementation with the help of continuous bag of word, and implementation with the help of skip gram. So both of these here we can see in the first and second. So this glow is outperforming to this continuous bag of word as well as to skip gram model. This was the idea, like the distance between the king and queen. This distance should be same as the distance between man and woman. The distance between king and queen should be same as the distance between man and woman. This is what ultimate idea behind glow. If we take another example, the country name and its capital, the distance is similar for one country as well as this distance should be same for some other country also, so that we can understand, okay, this could be the country or this could be the capital of that country. Okay, now we will see some deep representational learning. Here this is just an example of fully connected neural network. that probably you might have seen in that fundamental of deep learning workshop. Some input is given to us, we are detecting some features. Based on that, we are detecting some higher level features, and then we are recognizing the input. RNN is basically used for performing or for processing sequence models. Like some timestamps are involved. This is the input at timestamp t minus 1. Then this is the input at timestamp t. This is the input at timestamp t plus 1, like this. Okay. So this is nothing but the schematic of RNN cell, and this is nothing but the schematic of RNN cell in unrolled fashion. Okay. Then it generate output, and the state is passed to the next state or next cell. RNN is suffering from some problem such as vanishing gradient problem, long-term dependency handling. Then we introduced some of the other advanced architecture that can handle this RNN issues, such as long short-term memory. Then gated recurrent unit. Here you can understand this hidden layer is there and input is provided to us. Then everything is represented with the help of these two nonlinear activation functions, which is sigmoid and another one is tanh. So these concatenations are represented like this. And finally, three gates are there: forget gate, input gate, and output gate. So if we take an example of forget gate, which is responsible for forgetting something, like suppose if the information is not important, not relevant, then output of forget gate should be closer to 0, so that it can forget this information. If the input is or if the information is relevant or important, then we want that output of forget gate should be closer to 1, so that it can retain this information. So this is overall idea about every gate. Some CNN are also there. So CNN are not specifically in vision side, but it can be used in NLP side also. Ultimate problem was with the long sequences. When we look at the long sequences, then CNN, RNN, LSTM, these suffer from some performance issues. So basically, after that, we can introduce some other important metrics such as attention mechanism. So attention mechanism take care of long distance relationship between the words. So two types of attention that we can see over here. It's global attention, which is just considering all the global context. Local attention, in which we just define the predefined window, and based on that we will perform the calculations. This is the transformer architecture that we will see in detail in when we will see the lab of this part 1. Before that, we will, or otherwise we can just try to understand the things over here itself. See, at the time of model training, we are having input as well as output. Like suppose, just take an example of English to French conversion. Okay, so English sentence is given as input, and French sentence is also provided as output over here. But here the output is shifted one position right. Okay, output is shifted one position right. Then input is provided here. The very first thing is nothing but input embedding and the output embedding. So we convert this input sentence into embedding, like how these words are represented with the help of some word to back or glow. Then this output is also represented with the help of some distributional vectors. See, here we are not using any CNN or RNN model, so we need to introduce some temporal ordering. How can we preserve the temporal ordering? Like which word was there at third index or third place? Which word are there? Which word was there at 10th place? So we don't know. So to keep notion of this positional things, we introduce one more embeddings that is known as positional encoding. So this input embedding is get added with positional encoding. Ultimately, what we are doing, we are incorporating the positional information of each and every word into these representations. Here also we are incorporating the positional information with the help of positional encoding of every word in the output embeddings. Fine. Then these positional embeddings and input embeddings are get added over here, and then this information is passed to this multi-head attention. Fine. Now, before passing this information to multi-head attention, suppose here 10 words are there. Okay. Here suppose 10 words are there. Then each and every word is represented with the help of three vectors: query, key, and value. The sequence is like this: input is given, it is converted into embedding, then positional encoding is added into it. Now we are having 10 such vectors. Okay, 10 such vectors, because 10 words are there in that input sentence. Now corresponding to each and every word, we will convert that word into three representation. Every word is represented with the help of three vectors. First vector is query vector, second vector is key vector, and third one is value vector. Fine. How we will convert this? We will have some matrix. This this addition vector is multiplied to those matrices. So three matrices are there. One matrix is responsible for representing this Q, or one matrix is responsible for calculation of queries. One matrix which is responsible for calculation of keys. Third matrix which is responsible for calculation of values. These metrics are learned through the backpropagation or gradient descent process. Now we converted each and every vector into this three vectors. Every word. So first word is there. First word is represented with the help of these three vectors. Second word is there. Second word is represented by three vectors. Third word is there. Third word is represented by three vectors. After that, what you will do? You will perform this multi-head attention. So what operations that we will do, that we will see in that lab. We will once again come back to this. This was the first part. Just click on this launch button. I think when you use the event code, then you should be on this page. Then you should this code. So here in first part, three notebooks are there. These three notebooks. This is just an introductory notebook. In second part, once again, three notebooks are there. So these are the table of content. First, transformer architecture. This is the first notebook. Second, BERT, and third, pre-training the BERT model, pre-training language model. Just open the first one, transformer architecture. Ultimately, this was the thing when we are interested in converting English to French. So English input is there, which is provided, and encoder just encode everything, and then it is passed to decoder. Decoder decodes, and then it is generating the French word, a French sentence. This is the architecture, encoder and decoder. The very first thing is the tokenizer. When we pass input sentence, then tokenizer tokenizes this input. Okay, and ultimately what is does it just create the tokens of this, and moreover we can say tokens means the index of this token in the vocabulary. So this is what this tokenizer does. There are various tokenizer that are available for us to use. After tokenizer, okay, first see, this is tokenizer. After tokenizer, the second part is coming into this embedding part. This one, embedding. First tokenization, then embedding. So we are having word-to-vec, glow, fast text. These are several standard algorithms for converting the input into embedding matrix. Yeah, the next one was positional encoding. So do not go in the detail of this mathematics. The positional encoding is here. Positional encoding is introduced with the help of some sinusoidal functions. Okay. Uh, Based on this, we can introduce the positional encoding. You can just see run this cell by pressing Shift Enter, and we can just visualize this. So our ultimate aim is that we need to understand each and every component of the transformer architecture. So the very first thing that we will try to understand is nothing but the encoder part. See, when this transformer was introduced, then 6 identical layers are there. So 6 encoder layer as well as 6 decoder layers are there. So encoder size, 6 encoders and 6 decoders. See, this is nothing but one encoder. It is nothing but encoder number 0. So ultimately what we are doing, we are first converting this into tokens. These are my tokens. It is converted into embedding, means this is converted into vector, and then positional encodings are added over here. After this addition, we just convert this into 3 matrix or 3 vectors: query, key and value. So this tennis is represented with the help of 3 vectors: query, key and value. This ball is also represented with the help of 3 vectors: query, key and value of this ball. This was query, key and value of this word tennis. This query, key and value are provided as input to the self attention, and then we will see what this self attention do. Ultimately, this self attention is doing this. So if this playing and ball, okay, these are very much related, so this should prefer to high attention. And suppose just look at this dog and tennis, so it is having low attention, so some low attention should be reflected by this attention mechanism. Now what this self attention does, self attention performs the vector multiplication with query and key. Okay, so here see, query and key transpose, it is multiplied and then it is scaled by some dimensionality like dk, square root of dk, and then we apply softmax on this entire structure, and finally we are applying or we are scaling this value vector. This is the outcome of attention mechanism. So you can understand that outcome of attention is nothing but scaled version of this. Like suppose just see, two words are there. First word is tennis, second word is ball. So this query vector of this tennis, query vector of this ball. Okay, then this column, first column is indicating that key vectors of tennis, and then second column is indicating key vector of ball. These are multiplied, okay, and then it is scaled with the help of square root of dk. Then you are applying softmax on this, then these are the value vectors. First row is nothing but indicating the value vector of tennis, second row indicating the value vector of ball, and finally it is generating this z. Now multi-head attention, see, this was one head which is doing this. Here we are having multiple heads. Query key and value vector for first head, query key value vector for second head, query key value vector for third head, like this. And in their proposed architecture, it was 8 such heads that they used, and they call this particular layer as multi-head attention. Why there is a necessity of multi-head attention? So it might be interesting. One head is looking at some aspect of the input, Another attention might be looking at some other aspects of the input which are not specifically taken care by the first head. Likewise, there is a necessity of multiple heads. Then transformer decoder. So here we are having this decoder. First we have seen this encoder, self-attention, then it is normalized, then some feed-forward network is there. So this entire structure is known as encoder part. Just see here. This is my encoder number 0, encoder number 1, encoder number 2, 3, 4, and 5. 6 encoders are there, and 6 decoders are also there. In decoder, we are having two attention mechanism. One is attention encoder decoder attention, and one more is self attention, that is nothing but masked multi-head attention. So encoder decoder attention takes care of the output which is coming from the encoder side, and the input, actual input, that is coming from the decoder side. And mask multi-head attention is perform the masking of the input which is provided at the decoder side. Why there is a necessity of masking in multi-head attention in decoder side? Because it restrict the information flow in the leftward direction. What do we mean by this? Come back to this cell once again. So it prevents the leftward information flow. See here, this input is provided, and then it is generating the first word as output. At a time, only one word is predicted by the decoder side. Okay. Once it is predicting the first word, then after that, this first word is provided as input. Then it is predicting the second word. When first and second word are predicted, then these are provided as input, then it is predicting the third word. See, when we were training the model, then we are having entire entire French sentence with us. But suppose we are predicting the fourth word in the French sentence, then we should not provide the input from fifth word onward of that French sentence. So this is known as information flow in the leftward fashion. So that we do not want. Ultimately, what we want, that when fourth word of the French sentence is getting predicted, then only first three words of the sentence should be provided as input, and remaining all subsequent words should be just masked out. This masking is taken care by masked multi-head attention, and this is useful only when the model is getting trained. Because when the model is getting trained, we are having entire English sentence and entire French sentence is with us. Just click on that second one, that is nothing but bird. Now just look at this. BERT architecture is not having this decoder part. It is just having this encoder side. Basically, it is used for just representation of the input. The full form of this is bidirectional encoder representation of transformer. Bidirectional encoder representation of the transformer. So just it takes input and it represent. Efficient representation is done by taken care by BERT. Basically, two types of loss functions that they can use, that are used for by this BERT. One is masked language model prediction. So what we do here, one sentence is there, we purposefully mask any particular word at any particular index, and then we will try to predict that masked word. That is known as masked language model prediction. Next sentence prediction is, we provide two inputs. First input is nothing but the first sentence, and second input is nothing but second sentence. second sentence. We will predict that second sentence is these two sentences are in subsequent sentences or not. So if they are subsequent sentences, then our neural network should predict 1. And if they are not subsequent or consecutive sentences, then our neural network should predict 0. So this is the second loss function, which is nothing but next sentence prediction. Tokenization algorithm that it is used is word piece algorithm. Pre-training and fine-tuning. So pre-train BERT that can be used by us, and fine-tuning is nothing but how this pre-training is used for some downstream tasks such as uh, named entity recognition, text classification. Now we will see we are having this NEMO neural module, which is introduced by NVIDIA. So this neural module is a toolkit which just provide everything, and it is based on PyTorch Lightning framework. So it provide tokenization, it provide language models. See here. So we need to import NLP, and then we need to import BERT model. See, there are two versions of BERT model. Just see which type of BERT model are available for us. So BERT model dot list available model. Here we can see two language models corresponding to BERT that are used for us to first one is BERT base uncased, and second one is BERT large uncased. Okay, so he in first see in BERT only decoders are there. Decoders are not there. In first, it is a smaller model. It is larger model. In first model, 12 transformer blocks are there. Means 12 encoders are there. In second one, 24 encoders are there. First one is corresponding to 110 million parameters, and second one is corresponding to 340 million parameters. We will use the smaller one, that is BERT based uncased, and we will just use this model. Here see, we will see when we run this cell model. So the thing is that can we identify all the layers? How many transformer layers does the BERT base have? Hidden size? How can we identify key query value metrics? And which are the two loss functions? Just look at the outcome of this. This is BERT model, BERT encoder. Okay, encoder is there. This is first embedding. First one is word embeddings. Second one is positional embeddings. Then layer normalization dropout. These are some layers are there. This is the very first encoder. Okay, it is known as BERT layer, first layer. Here we are providing self query key and value pair. The matrix of size is this 768 and 768. Okay, this is my first encoder, 0 number. Then it is producing some output, then some dropout is there, then some intermediate of that encoder, then finally this is the outcome. This was first encoder layer. Now this is my second encoder. And how many such encoders are there in the smaller version? 12. So index number 0 to 11. These are the 12 encoders available with us. This is last encoder. After last encoder, some pooling layer is there. Now we will see two loss functions. This cross entropy loss mask language model, and this is next sentence prediction. So these two loss functions are there. We will see how many parameters are associated with this. This something 110 million parameters. Now word piece tokenizer. There are three types of tokenizer: character level tokenizer, word level tokenizer, or subword level tokenizer. Basically, it's a subword level tokenizer. Example of subword level tokenizer is this. See, if we take the word tokenization, okay, so character level will just recognize the character TOKEN. Okay, word level it just recognize one word for tokenization. But the word may be like this: tokenizer. Another word may be tokenizing. Third word may be tokenization. But if we take word level, then these three embeddings should get generated. But these three uh, words related to token only. That's why we go for subword level. So token is one thing and another one is ization. So suppose tokenizer is there. So token is identified as one token and izer is identified as second token. Tokenizing. So token is identified as one token and izing is identified as second. So subword level tokenization is very important and very effective. Algorithm basically it just uses that subword level tokenization, and first it start with character level, then it just identify which two characters are coming or co-occurring with each other, then it just club these two characters and perform these steps repeatedly. Which type of tokenizers that are available with Nemo? So these are the various tokenizers that are available. So we will see here two tokenizer are there: bird based uncased. We just take this tokenization. The vocabulary size is 30,522. These many words are there. Okay. Like suppose if we take this sentence, then we can see the outcome of this. See, this is uncased. So this capital H is recognized as small h only. Small h will recognized as small h, but capital H is also recognized as small h. Okay. So we are having one more tokenizer, which is nothing but bird base cased. Okay, so which recognize the capital and which differentiate between capital H and small h. We can also see the index of capital hello. So here two hello are considered. This hello is different than this hello. So index of this hello is this and index of this hello is this. First first it is printing the output sentence and then it is predicting the tokenized sentence. Okay, you can see the solution. Then contextualized word embedding. Basically, contextualized word embedding is nothing but when the words are similar, they should be closer to each other. If we take an example of this, wireless mouse was eaten by an animal such as mouse. Just look at this sentence. This mouse and this mouse should be different. Here we are talking about that computer mouse, and here we are talking about that rat. Okay. Now just look at that. This type of embeddings are known as contextualized word embedding. This mouse was said in some different context and this mouse was said in some different context. If we would have generated only one embedding for both of these mouse, then something different or something wrong would have happened. So this should not have done. We will see the outcome of that BERT model, and we can just plot this with the help of TSNE. See here, this is mouse computer 1 and mouse computer 2. They are same because they are closer. Here another mouse animal is there, which is red, which is far apart than this two mouse. We are having one standard process to represent this. TSNE is the algorithm. So we can just have a plot of this. Now we can go to the third notebook. See, third notebook is based on some data preparation. Two types of data that are available with us: on the fly data pre-processing and offline data pre-processing. So basically data is available with us, then we can if the data size is small, then we can go for on the fly data pre-processing, or otherwise data is there in some other formats that, like suppose HD5 file, then we can go for some offline data pre-processing, because data pre-processing itself is a very large step. See here, some data is available with us. Data train txt. This is my data. Train txt is there. Okay. Just see which type of data is this. Here it is nothing but NCBI corpus. NCBI corpus is nothing but some 793 PubMed abstracts are there. It is related to medical fields. Okay, so this is my first abstract, then this is my second abstract. Likewise, total 793 abstracts are provided in this training data. Now we will see training the BERT tokenizer. First thing is that how we can handle the out of vocabulary problems. uh, Suppose one word is there which is not there in the vocabulary, then we can define that word as unknown. But the problem is, uh, dog is also not there in the vocabulary, cat is also not there in the vocabulary. Then both of these words will map to the single special token which is unknown. So that should be wrong. On the other hand, we can go for character level token, but it will increase the size of the neural language model. Another word is subword level tokenizer. So that is effective. We can go with the subword level tokenizer. See here, the tokenizer size is this 30,522. Okay. Now we will predict the index of these tokens. See, 2019, 20, 21 is recognized, but 2022 is not recognized. 2023, after 2021, it is not recognizing 22, 23, etc. Okay, so here we are using subword level tokenization. 202 is recognized. Okay, and then this is the last remaining part, hash hash 2. 202 is there, hash hash 3, 203, and hash hash 0, like this. Now suppose we take one sample. Here see, two words are there, dilution and this hemolytics. These are very specific to a medical field, so these are not recognized because these words are not there in the vocabulary. But we can add these words in the vocabulary. How we can add these two words in the vocabulary? See, this is my COVID-19 text. We can just copy this text. We will see how COVID-19 will be taken care by this. Just run this cell. COVID-19 is not recognized. O is one token, VID is another token, and 19 is another token. Now we can update the word vocabulary. We can add these two tokens. See, we can add these two tokens, dilution and hemolytic. And after that, once again, we will predict the vocabulary. We will print the vocabulary size. Previously, it was 522. After adding these two tokens, the size is 524. See here, now hemolytics is recognized. Hemolytic, then dilution is also recognized. But this is not the exact way. We are just adding the tokens and then we are recognizing it. Ultimately, new model on this particular train.txt. So what we can do, we just take the vocabulary size as 10,000. Okay, then these are our special tokens. And we need to provide the text corpus. So text corpus is this train.txt, and then once again retrain the tokenizer. First of all, we need to we need to import this tokenizer. So this is the BERT wordpiece tokenizer that we are importing. We are taking the instance of this BERT wordpiece tokenizer into my BERT tokenizer, and then once again we are retraining this my BERT tokenizer dot train. What files we are passing it to this train.txt. Vocabulary size is 10,000. Minimum frequency is special tokens. Progress, this we will pass. Now the model is trained. We will see we train this tokenizer, my BERT tokenizer. What is the length of this? 10,000, because we already defined this. See here, vocabulary size is this 10,000. We can train this model, and where it is getting trained, in data folder. Just see, when I save this, then one more model should get saved over here. The name of this model is vocab.txt. See, vocab.txt. This is my tokenizer. We can also print some of the initial tokens. These are the initial 20 tokens that we are printing. Then these are some special tokens. So here it will recognize, it is recognizing all the medical types of terms, medical terms which are there. We can train a larger model. Previously we take that 10,000 was the vocabulary size. Here we can see now this time we are taking it as 15,000. We can train a larger model. Next, how we launch BERT pre-training with Nemo. We are having two file. One is that YAML file, and another one is this Python script. This YAML file is nothing but having three things: trainer, experimental manager, and model. Okay, so we can just use those trainer, experimental manager, and model, and we can just update this. Training script is nothing but that automate everything that is required for this running the configuration file. So for with every model which is there in Nemo, two files are associated. One is this config file, another one is this training script. It contains all the parameters, parameter related to model, parameter related to trainer, parameters related to experimental manager. We will see this in detail in the next notebook. See here what we are writing. We are just printing this BERT from text config. So these are the trainer details. How many GPUs are there? How many max epochs are there? What is the precision? What is the automatic mix precision level? Trainer. After that, some models are there. Then lastly, see which type of validation data, which type of training data. Then lastly, this experimental managers are there. Okay. Now you can go to this assessment question and just look at that how many questions that you can solve. You just look at that these questions can be solved. Some of the questions can be solved because some of the questions are based on second notebook and third notebook. And we will take half an hour break. We will once again start at 11:30. Then we will look at the second one, and simultaneously we will be looking at the assignment also. The answer of question 2. See, attention is all you need. So because RNNs are no longer required for sequence modeling in such tasks. This is one answer. Another answer is because multiple fewer sequential operations results in greater parallelization when processing this model. The relationship between the words that are sequentially farther, uh, that is having larger distance, that can be inputted completely with the help of this attention mechanism. LSTM layers combined with self-attention layer create a robust. So this is not applicable. Then attention mechanism transformer architecture. What is the purpose of attention mechanism in the transformer architecture? So it do the input sentence and decide at each step what other parts of the are important and input that information. We have seen that slide in which tennis was recognized, or tennis was very closely related to ball, playing was very closely related to ball. Okay. I think there are total 6 questions, so you can just look at some other questions also. So we will also see this in the next round when we will start at 11:30. Hello. Yes, is the screen visible and am I audible? So you can see I need to launch the second thing like self supervision, BERT, and beyond. And the complete final assignment is based on this. So simultaneously, we can also have a look on the assignment also, or probably we can have first look at the presentation, then this notebook and the assignment, coding assignment. Fine. Okay, so here we will have a look at self supervision, BERT, and beyond. Now just look at that. What do we mean by self supervision? See, every time we are not having that labeled data with us. Okay, so this time we have devised one mechanism so that supervision come from the data itself. When supervision is coming from the data itself, then it is known as self-supervised data. So what do you mean by that? Supervision is coming from the data. Like suppose, see, if we are having an example of a valid sentence, okay. So this valid sentence is having several words in that sentence. What I will do, I will mask any particular word in that, and I will predict that word. Okay, and because when I'm masking that word is already known to me. Okay, and when that word is already known to me, it means that that can be act as a label data for our prediction model. On the other hand, if you take another example like English to French language conversion, so when we are having that French sentence with us, then we can say that some of the supervision is coming from the data itself. So when we are having a very limited amount of data like French, English to French conversion, then this can be act as a self-supervised kind of learning. See, the first example is this masked language model. Then the second one is next sentence prediction. So what do you mean by that? This next sentence prediction. One sentence is there, then another sentence is there. That another sentence is following this current sentence is or not. Okay. Then we can train a model. So for that we can take any Wikipedia corpus, and from that Wikipedia corpus we can give the input consecutive sentences as well as non-consecutive sentences. If we are giving consecutive sentences, then we are already having that label as one, and if we are not taking non-consecutive sentences, then the label is zero. So in this way supervision is also coming from the data. That's why we call this problem as a self-supervised problem. This was in the context of natural language processing side. Another we can see in the context of computer vision side also. In computer vision side, we can randomly crop any particular portion of the image and try to predict that cropped portion. So because we are already having that cropped portion, so that cropped portion that we are having will act as a label. So that's why here also supervision is coming from the data itself. So these are the various examples of self-supervised learning because we are having enough amount of data with us. So we cannot ask for the annotated or labeled data set for the entire data that we have, so that we can go with this self-supervised kind of learning. Data is already abundant amount of data is available, and we need to just figure it out the supervision from the data itself. This is what the overall idea behind it. Yeah, this is the scaling laws. Here, some small data set is there. If the training data set size is very small, then the generalization loss is error is very large. And this is nothing but power law. When training data set is increasing, then error is getting reduced. After some point of time, for reducing the error, we need lots of data available with us. So this is what known as irreducible error region. Now come back to that notebook. Okay, I think it is taking some time to getting it loaded. Uh, have all of you have launched this notebook? Fine. Next, we will see what do you mean by GPT, generative pre-training. See, previously we have seen one example of pre-training fine-tuning when we were looking at that fundamental of deep learning course. But this time of we are looking at generative pre-training. Like our model was
Screen is not
perfect.
visible.
Yeah, now it is visible. Fine. So just go to this course and launch this.
So your screen is still not visible, showing the loading sign.
I think I need to reload this. Now is it visible?
Yes, the screen is visible.
So fine. You can see this notebooks. Here we will try to understand the first and second notebook, and then we will go back to the final assignment that we have for this particular workshop. Is the screen visible perfectly?
Yes, yes, it's visible.
Fine. See, this is just an introductory notebook. Here we will see some pre-training data pre-training is available with us. So this BERT model is there, and then this is pre-training loss. Okay, so this was my pre-training. But after that, what we can do, this pre-trained model can be used as a fine-tuning for some other downstream task. So data fine-tuning is there, then BERT model is already loaded from here, and then some additional layers are there, and finally fine-tuning loss is there. So this is nothing but fine-tuning process. There are three parts. First one is exploring the data, second one is build a text classifier, and third one is building a named entity recognizer. So see here, this is the first part. We will see NCBI corpus that we will see. First, just double click on this explore. We will try to explore the data. NCBI disease corpus is a set of 793 PubMed abstract. See where this data is there. In this data, three things are there: NCBI corpus, the raw corpus, then NCBI for text classification, and NCBI data for named entity recognizer. These second and third, these folders are derived from the first one, NCBI corpus itself. And what is there in NCBI corpus? The PubMed abstracts are there, and how many PubMed abstracts? 793. In this, they have introduced the disease in the form of this modifier. Just look at this. HTML style tag is inserted. Suppose if some disease name is found there in that PubMed abstract, just look at this. Suppose this is category modifier. So this is one disease name. Okay, and then this is the category closing. Then another category is this. Then another closing of this category. So this type of HTML tags are inserted for well annotating the data. And then we will look at that how many things are there in NCBI corpus. If we just double click on this left hand side panel, NCBI corpus, three things are there. First one is training text, another one is testing text, and then development text. If we take an example of sentiment classification, so two types of possibilities are there, whether the sentiment is positive or negative. Likewise, here we need to build a classifier, but it is a multi-class classifier for this PubMed. So three possibilities are there. Given a medical disease abstract, so we will be given one abstract with us. We need to figure it out. If is the abstract about cancer or neurological disorder or something else. Three possibility. Category 1 cancerous, category 2 neurological disorder, and category 3 is something else. Now just see, we are taking this directory. Okay, which directory? Then data NCBI text corpus 3, data, then NCBI TC3. Okay, and then we will print what is there in this directory. So three CSV files are there, sorry, TSV files are there. TSV files are nothing but tab separated value, tab separated values. Like first word would be there, then one tab, then second word, then tab, then third word, like this. So three TSV files are there. We will see which type of data is this. So we will print some of the initial rows. See, this is what we have printed. This is my first entry. Then sentence is this and label is this. And just tell me how many label would be there? How many label would be there? 3 label. First category is cancer, label 0. Second category is neurological disorder, category 1, label 1. And third one is any other, so label 2. But what we need to do, we need to just remove this sentence and label. We do not want this header. We need to remove this sentence and label. We are just interested in the exact actual data. This is my second entry, label is 0. Third entry, label is 1. So this is neurological disorder. Previous two were cancer. Test data can also be explored in the similar fashion. So here we have explored the text classification data. Now we will explore the NCBI data for named entity recognizer. So here this is my data. This is named entity recognizer. Now I will briefly see what is there in this NER data set. So ultimately what we are doing, we are taking one pre-trained model, and then those pre-trained model are first used in text classification, and then secondly used for named entity recognizer. This is my training data, and then see, these are my training labels. Here we can see some IOB taggings are there. What do we mean by IOB tagging? That we will see over here. See, suppose this is my text. Here it is named entity. Here we need to identify the tokens related to the disease. Just look at that, where the disease name is getting started. Here the disease name is getting started. So here inside, sorry, beginning is this. After that, some words are there which is also related to the disease itself. This entire thing is nothing but our disease. Okay, this is my beginning, and this is inside of this, and remaining all are outside. That's why three types of tags or token names are inserted over here: inside, beginning, and outside. Beginning indicate that the disease name is getting started. After that, some other words are also there uh, subsequent to that disease name. Okay, so we will call this as inside, and remaining all entries would be outside. Then just look at the second thing, text classification. So here we will build a text classifier. Nemo is built based on neural module, and which is ultimately based on this PyTorch Lightning. Basically, it's a PyTorch wrapper which organizes the PyTorch code for the neural network training. Here it is having two modules, Lightning module and Trainer module. Lightning module is used to organize the PyTorch code into this computation, optimizer, and loops for training, validation, and test. And trainer is then able to take this Lightning module and automate everything that is required for deep learning training. So Nemo model, every types of models that are available for us to use in this NVIDIA Nemo GitHub repository. So here we are having text classification model, token classification model. So here we will see which type of models that are available for us to use at up to level 2. See, these are NLP models. First model is dialogue tracking. Second model is entity linking. Then glue benchmark. So these are the models available with us. In every model, you can see one configuration file, config.yaml, and one training script is there. So among these model, which model that we are interested in using? We are interested in using this text classification model. In text classification model, this is nothing but our training script, text classification with word, and this is our configuration file in this config folder. Okay, so we will take this DLI task Nemo example, and this model we are taking as our model. Then just run this cell. See, in this classification model, we are having one folder config. In this config, we are having configuration file, then data is there, and this training script is there. Fine. With the help of this configuration file, we can override the values such as model configuration, and then this training script will be run free after that. Once the values are overridden, basically it employs Facebook Hydra tool that automate everything for this training script execution. Now we will see how we can perform the text classification from the command line. Okay, we are having three categories: cancer, neurological disorder, and other. Then see, this is my text classification directory where it is this data and then text classification. Three files are there. Then next thing is that we need to take a look at the tab separated values. See here we can see sentence label, but this sentence and label that we do not want, the pre-processed data is already in the form of word, then tab, word, tab, like this, and then finally last label. Here sentence labels are also there in the header row, that should be removed, and maximum sequence length that we need to define. What do you mean by that maximum sequence length? See here we can see this is the abstract. In that abstract, suppose 1000 words are there, so we are not interested in processing that 1000 words, so that then we need to define that maximum sequence length. So if we define maximum sequence length as 256, then initial 256 words are taken care of, and rest all will be ignored simply. So first of all, I need to remove that sentence label. So for this, I need to use this command. 1D means the first header row should be removed, and then it will be stored in this file, train nemo format.tsv. Nemo format means that is compatible for neural module. Previously, it was there in this train tsv, test csv, and dev tsv. Just run this cell. So three more files should be created after this. See here, this is dev nemo, test nemo, and train nemo. It is compatible with the nemo format. Now we can once again print this. So I think the label will not be there this time. See here, labels are not there, directly text is coming. And this is everything in the folder of this NCBI text corpus 3. Total 6 files are there. 3 are in the original format and 3 are in the Nemo CSV format, Nemo TSV format. Now we will see the configuration file. This time we are having that configuration file, text classification config.ml by ML. In this configuration file, we are having three main things: trainer, model, and experimental manager. In trainer, these are the things that can be overridden. In model, these are the things that can be overridden. In experimental manager, some more things are there. We can override each of these values. For that, first of all, we need to see the directory. This is my directory, text classification.config, and configuration file is this. Dot, I need to just concat these two, and here we can see this. These are the things which are there. Trainer, GPU, one number of nodes, max epoch, max steps. All these are the attributes of this trainer. This automatic mix precision level, then precision 32, accelerator. Okay. Then second thing is coming as model. In model, what is there? Nemo path, tokenizer, which tokenizer model that we are using, which language model that we are using, classifier heads, class labels, dataset, which dataset that we are using, how many classes are there in the dataset. Suppose I need to modify the number of classes, then how can I modify? That model.dataset.num classes from that command line. Then training dataset, training DS, what is the batch size, then validation DS, test DS. Is there any optimizer that we are using? And lastly, experimental manager. We just record all the logs. Omega config tool is there. From this Omega config tool, we can easily access and manipulate the configuration keys with the help of a dot protocol. See here, we first need to import this Omega config tool, and then we need to load this Omega conf dot to IML. So here we are printing config dot model, but three things are there in config. One is model, another one is trainer, another one is experimental manager. So we can print model, we can print experimental manager, we can print trainer. Here we are printing model. See in model what is there? Tokenizer. This tokenizer that we are using, language model, everything is there. Here we are printing the trainer. Here we are printing experimental manager. Then we will see what do we mean by Hydra enabled Python script. See in what we need to do. These are the exercise that we need to do. Number of classes that we make it to 3. Then maximum sequence length that we are taking 128. Then train DS where the training dataset is there. So we need to define this directory, this path, validation DS, this path, test dataset, this path. Some inferences sample that are already that needs to be provided for just evaluating how it is giving output on the sample inferences. Then max epoch, which is set to 3. Now see, this is how we can train or we can run the Python script. Two things are there in that model. One is configuration file, another one is training script. Here we will be running training script, and we can also see how we can override the configuration value. So this is my training directory. Number of classes 3, maximum sequence length is this, path, train nemo format, dev nemo format, test nemo format that we are providing over here. Then these are inferences sample, max epoch. Now see, we are running this training script file. In this, we are just overwriting model.dataset.number of classes, model dot. So these things to model, and for how many epochs we are running? For 3 epochs. This number of epochs is coming under this category of trainer. 3 things are there: model, trainer, and experimental manager. So these things can be updated with the help of model dot attributes, and the last thing can be updated with the help of trainer. Just run this. It will take some time to train. So this is getting trained. Now fine. Just see what is there. And at the end of this training, Nemo neural module save the last checkpoint, means the last updated values of the model, like at the specified path. And which path is specified? Model.nemo file path. Okay. And here we can print .nemo over here. See, these are the things that can be printed out over here. This Nemo folder is there. I think it is getting run. So see, this model is saved over here. The name of this model is text classification model.nemo. It is stored here, text classification model.nemo. Now run the experiment. See, this automatic mix precision level can be set to O1, O0 or O2. We can use some mix precision with the help of O1, and we can just we just need to perform the operations in some reduced precision, so that we can use less amount of memory, and the computational speed can be improved. Here we can see the solution. These things can be updated. AMP level, automatic mix precision level, precision 16, and learning rate is this. What it is asking for. Override the config value in the command line. How can we override the config value like this? We need to run the Python script. Just run this. So with this, you can override this trainer.max epoch. Suppose automatic mix precision level, that can be updated like this: trainer.amp level, then $amp level, trainer.precision, and then trainer.learning rate is this LR. So we just uh, copy all these things, and we need to, then we can run this. Now see here, so far we are using BERT model, but we can use, there are several other models also. So we can change the language model also. So for that we can just look at this, how many models that are available with us. And if some good model is there, then we can use that model also. Like suppose we are having this Megatron BERT 345 M case. So this is a model which is large, which is very much compatible with the medical type of data available with us. So we can use this model. And here we can do the same thing with the help of some different language models. So is everything clear in this notebook? Then we can move to that assessment part, and we will try to understand the things at the assessment. You can just stop this task, then only you can launch this assessment coding project. All of you are required to stop the current task and just launch this assessment coding project. All of you are required to launch this assessment coding project by just stopping the second tab. All of you have launched that assignment. So you can simultaneously solve that assignment with me. Yeah, it's still loading. I think 2 to 3 minutes it will take, and then we will just have a look at the assignment and what needs to be done in that assignment. That assignment is very simple. Once we can correlate the current notebook that we just solved with the help with that assignment, then everything would be fine. So I think it is loaded now. So you can now launch that assignment. So everybody on this page, or should we wait for 1 or 2 minutes? So you can just see it is a case of it is an assignment of authorship attribution. Authorship attribution. What do you mean by that? See, one paragraph or one document is given to you, and we are interested in identifying whether this document has written by this author or by that author. Are you getting the problem? One document is given to us, and we need to just figure it out that who has written that particular document, the author one or author two or any other author. Are you getting the problem? Yeah, you can just unmute yourself, and then this will be an interactive session. If any doubt is there, then we can have a discussion on that.
Yes, sir.
Fine. Now see, these are the table of content. These are the steps. First, we need to prepare the data, then prepare the model configuration, then prepare the trainer configuration, train, infer, and submit the assignment. 6 steps are there. So I will not tell you the answer. You just need to figure it out what could be the answer, and then we will have discussion on that. So two authors are there. We need to just figure it out whether the document has belonged to author one or author two. Our data is there in this folder train.tsv, development.tsv, and there 10 data sets are there, and we need to just test or evaluate it on our 10 data sets. Data sets are contained in the folder data.federated. See, this is data folder, and in that Federalist papers, in which our this data is there. This is my train.tsv, training data. This is my development, and finally these are some testing files. See, each sentence is actually a group of approximately 256 words. The label are 0 for Hamilton and 1 for Madison. 0 for Hamilton and 1 for Madison. So how many authors are there? How many authors? Yeah, two author. You can type in the chat box. That's fine. And then the validation set is there. Fine. These are the scoring. So here a number of fixed me's are there. Number of fixed me's 2 in the first step, 3 in the second step, 3 in third step, 4 in the fourth step, and 0 fixed me's are there in fifth step. And these are the points. Total points are 70. This model that we will be using, text classification with bird.py, .python. Then, okay, these are the resources and hint. See example code. So lab2 reference that you can take as example. Language model. So basically, we need to use some case language model. So this should not be uncased. Like suppose there is a possibility that author 1 is using uppercase or author 2 is using lowercase. That's why our model should take care of this cased document. Maximum sequence length should be 64, 128 or 256. Lower is good. Larger model that also can be used like BERT large, Megatron. But if we are using larger model, then we should use maximum sequence length as 64 or smaller. Number of classes. So only two classes are there, Hamilton and Madison. Batch size, that we can take how many samples could be there in one batch. Generally it should be small, 16, 13, 32 like this. If we get some error like this, CUDA runtime out of memory, then what we can do, we are not accommodating everything in the so we are not accommodating everything in the memory, and then we can reduce the batch size, or we can reduce the this maximum sequence length. Accuracy, it is definitely possible to achieve 95% or more model accuracy for this project. In addition to changes in the accuracy as the model train, pay attention to the loss value. You also want loss value to be dropping and getting very small for the best results. Number of epochs that we need to decide upon. Now the first thing, prepare the data. Is there any what we are doing, importing the utilities for grading. So this needs to be run as it is. Just run this. Nothing has to be fixed over here. Where the data is loaded, in this data directory, Federalist Papers. These are the files that are available here, TSV files. Now just have a look. Complete the fix me. We need to get the data in Nemo format. So what needs to be done here? What needs to be done over here? We had already seen how to get converted into Nemo format. This is what we did. Train TSV, dev TSV, and test TSV. When we write this statement, then it will get converted into Nemo format, like just removing the headers. So here, when we come over here, then the data is not in the correct format for Nemo text classification. Correct the data and save the new data set in this data directory as train Nemo format.tsv and dev Nemo format. See, we need to convert the training and development data only. You do not need to do anything with any of the test file. So only two things that needs to be fixed. So you got what you need to do and how it can be done. Here these two fix me's are there. You can try and just let me know whether you can do it or not. This is the cell. So what you can do, you can just copy these two, training and validation. You can go back over here. But what we have defined, data. Yeah, this is my data directory. Fine. The name is data directory. We need to copy this name, data directory. This time it is not TC3 data directory. Here the name of this file is same. I think it is train.tsv. Train.tsv is file, but this should be data directory, and this should be data directory, data directory, and here also data directory. And the format is this. The name is this train nemo format, train nemo format.tsv, and dev nemo format.tsv. Is it looking fine? Is it looking fine? Should I run this? Okay, so just see how we can run this. So it is running successfully. We can print some of the rows for this train and development. See, header files are removed. This is first author written, and it is belonging to Hamilton, first author. Then this is text, which is belonging to first author Hamilton, like this. Now run to save for assessment. Here no changes should be there. Just run the cell as it is. Now the second step, prepare for model configuration. Prepare for model configuration. Which model that we are interested in using? Text classification. So this is my configuration directory. It is there in Nemo, and this is my configuration file. I just need to concatenate both of these, and I need to run this. Text classification. Here we can see which model that we can use over here. These are the various models that can be used. Megatron BERT, Megatron based, BERT uncased, BERT based uncased, BERT large uncased, BERT base cased. So here they have defined, they have mentioned that we need to use cased model. So BERT base cased or BERT large cased, that we need to identify. Now here we need to set the parameters. These fix me should be clear. How many number of classes, what should be the maximum sequence length, and what should be the batch size. This is path to training file, path to validation file, and pre-trained model name. If we can change this, or we can just let it be as it is. If we will see if it is not getting correctly generating the output, then we will change it to BERT base cased, or otherwise we can just change it to BERT base cased. Just remove this un from here, then it will be BERT base cased. This is my learning rate. Fine. What? How many number of classes are there? 2. Yes, fine. Then maximum sequence length, that we can take it as 64. Batch size is, we can take 16. This is just hit and trial. We will see whether we can accommodate everything into memory, and we will get the desired performance or not. Otherwise we need to just change the parameters. Okay, just run this cell now. Then this was step 2. Prepare the trainer configuration. First we will see trainer, and then we will see the experimental manager. Trainer configuration. So for how many epochs that needs to be run, what should be the automatic mix precision level, and what should be the precision. See how we can define this. We can see the previous notebook. See this one. How we can define this? Max epoch is can be defined as 5 or anything. Then automatic mix precision, it can be defined as O1, O2. Reduced precision that we will use as 16. So here max epoch should be, we can write over here as 5. Then AMP level, that can be written as O1, and this precision can be written as 16. Just now the fourth step is train. Complete these fix me's. What should be written over here? The first thing is that we need to define these 4 things over here. Which 4 things? Max epoch, AMP level, precision. What about learning rate? Learning rate also we defined. This is learning rate. Then we need to define these 4 things. Fine. And how we can define this? So something should be there in model, something should be there in trainer. So these things like max epoch, AMP level, and precision, they should be there in trainer, I think. See, trainer dot max epoch is equal to this trainer dot AMP level, trainer dot precision. Learning rate is defined over here, model dot optim dot learning rate. Just define these 4 things over here and just run this. Just do it and just check whether you can write the things or not. Yeah, the 4 things are that we just define now. No? This one, max epoch, AMP level, precision, and learning rate. Learning rate. See, you can also change the maximum sequence length. Maximum sequence length is 64, is very small. 256. Maximum sequence length is 256. And you can also increase the epoch. Keep it 10. See, learning rate, max epoch, then learning rate, max epoch, trained yes, batch size, training batch size, validation batch size, AMP AMP level and precision. You just need to define these four things. You can take the help of previous notebook. We will take a break of 5 minutes and then we can continue. So I think you can. I think how many of you can do it? Have completed this? You can take another 5 minutes. No, I think you should not get error. Probably you have written something mistakes in the syntax only. It will be a very minute mistake. Make sure that you run all the previous cell properly. See, how many of you are getting error in fourth step? Yeah, we need to just run the fifth and sixth cell. All needs to be Hamilton. Yes, right. Every output should belongs to medicine. Yes. Epoch you can take 10. For 10 epochs you can run. No, just wait. I will check. No, there is some little crux is there that you need to figure it out. See, I can share the solution, but it will not be good. Probably you should be come up with a proper uh, solution. There is a very small mistake that everybody is committing. I just got that mistake. You can try. Probably you will get this. Yeah, AMP level O1, capital O and 1. The maximum medicine should be there in the outcome. If you get maximum medicine, I think 9 out of 10, then also it would be fine. How many of you are getting 9 medicine or 10 medicine? Okay, just a minute. I am sharing the screen. No issue. Yeah, is the screen visible? Is the screen visible? Fine. See total how many things that we need to define it over here. See this number of classes, maximum sequence length 256, batch size is 16, learning rate that we need to define. Okay, then trainer configuration, maximum epoch 10, AMP level is O1, precision is 16. Train. See, so till this point it is there. Then this is the first thing. Sorry, trainer dot max epoch, then trainer dot AMP level, trainer dot precision, trainer dot optimal learning. Sorry, model dot optimal learning rate. See, you. I think you forward to defining this batch size. How many of you have defined this? What is the batch size of training data set and what is the batch size of validation data set? Have you defined this? Then also you are not getting the correct output. No, I think it should not be done. I think it should not happen. What is the epoch that you taken? Max epoch. Just you can